This hopefully brief presentation provides some elaboration on a few of the objectives for Part 2 that I think are very important to pay closer attention to, and it also provides more context for some of the other objectives and some of the other information and examples presented for those objectives. Now, Part 2 focuses on quantitative research models, and you'll notice on the title here that I have positivist in parentheses. Just to remind you from Part 1, positivist research, or at least the positivist philosophical approach to research, is typically a deductive models, and the models typically involve making observations that are quantified in some way. That is usually turned into some kind of number. And some of the common research designs in positivist research include some non-experimental designs that we'll briefly discuss, pre-experimental, experimental, and quasi-experimental. And those are all some models that I'm going to go into a little more detail in this presentation. So that is positivist research. And I want to tie what I'm going to be talking about to something that was part of the very first project that you did last week in the class, and that has to do with the Virginia Literacy Act. And I just want to remind you that in the Literacy Act that goes into effect in just a couple of months in the state of Virginia, that evidence-based literacy instruction is referenced throughout the entire Literacy Act. So they're looking for evidence-based instruction, and what is meant by evidence-based is that there have been observations made that the instruction that is going to be used in the classroom it is or can be effective at accomplishing the instructional goals of the teachers, the literacy goals. So evidence-based is all about observation-based. And one thing that I was thinking about is why did they enact this act? Because obviously there was some dissatisfaction with the way things have been going in the state of Virginia regarding literacy. So one thing that I did is I went to the data on the Virginia Department of Ed website, and I got the percent passing rate of third graders on the Virginia SOLs for reading. And if you take a look at this graph illustrates that scores from the 2005 was the last year the earliest year that they provided data on. So that was 19 years ago. And at that time, the percent of third graders who were passing the reading SOL test were between 80 and 85% for a good 6 or 7 years, and then it just dropped. And it dropped pretty significantly. You can see between 2011 and 2013, the passing rate for third graders went from 85 down to below 70 in the 60s. And it went up a little bit, and then it just sort of continued to decline. And there was a significant dip in 2020, and I think we can all sort of guess why that is the case. But we seem to be on a continued downward trend for reading pass rates. And of course, there can be a lot of reasons why that's the case. You know, if you think about it, what's the cause of that? It could be that we've got new teachers who aren't as prepared at teaching literacy, or they're newer teachers. Older teachers left, retired, and newer ones came in, and they're just not as practiced at it. That could be it. It could be that schools adopted something in 2011 that was different than what they had before, and it just didn't work very well. It could be that the characteristics of home life in 2011 have changed dramatically. It could be related to socioeconomic factors. It could be lots of things. But the Department of Ed has decided to try and accomplish, or at least try to make a change that they do have some immediate control over, and that would be changing the type of instruction that is used. Now, one of the things that you are going to learn more about in part 2 is there are some research models that are non-experimental at trying to answer the question. So if the question is what factors are influencing the decline of third grade reading SOLs, you can correlate the data that is presented on this chart with other factors to try and figure out if there's a significant relationship between those factors. And it would be easy to correlate the average years of experience of third grade reading teachers, or first, second, and third grade reading teachers, and these scores. But you have to be careful about correlation because as was asked in one of the questions in the Project 1, the difference between correlation and causation is that correlation simply indicates that there is a significant relationship that two variables change together. It doesn't mean one causes the other to change. It means it changes together. And causation would be that you can definitively say that one variable caused another variable to change. So that's the primary difference between those two. Correlations, though, can happen to random variables as well. That's why they have to be taken with a grain of salt. For example, there's a great website online that presents all these what they call spurious correlations, and here we have a significant correlation between the divorce rate in Maine and the per capita consumption of margarine between the years 2000 and 2009, and you'll notice a downward trend there. And actually, if you look at the reading SOL pass rates at between 2005 and 2009, it's fairly steady. So I would suggest that there's no correlation between the divorce rates in Maine, the per capita consumption of margarine, or the reading performance on SOL tests for third graders in the state of Virginia. And I could be pretty confident that relationship indicates that that none of those variables are related to each other. But so that was something that was part of Project 1 that you were asked to consider, and correlational research is discussed in part 2 of the class. Now, the first objective that I wanted to elaborate on from part 2 is that you should be able to identify and describe some primary reasons for employing non-experimental designs in educational research. So why would you do non-experimental if you wanted to do quantitative research or positivist research? Well, first of all, non-experimental designs are appropriate when you don't have any independent variables to manipulate. For example, if you were to investigate scientifically an answer or a possible answer to the question, why have third grade SOL reading scores dropped over the past 5 years? So you would be examining data that already exists, historic data, and you'd be looking for factors that might correlate or might indicate some causation due to some type of investigation and perhaps some type of statistical evaluation. Another research question that would require a non-experimental approach would be, how do students use AI resources at home? If you were interested in that because you were interested in studying more about AI in the classroom, this might be a really interesting and important variable to consider right now, or question to consider right now. But you'll notice that you're not going to be manipulating any variables at all if you were to try and investigate an answer to that question. And finally, another unrelated question a research question that would not be approached using a scientific or using an experimental approach would be, how relevant are high school biology topics to the personal lives of students outside school? Now, it seems to me in answering that question, you would want to have high school biology students as your subjects, and you would be interviewing or surveying students about relevancy with respect to a variety of topics that are addressed in the class. So In that case, there are no variables manipulated. You're simply collecting observations, and you will be analyzing those observations. So those are some good examples of research questions that would not require or would not necessitate experimental models of research design. And so the course notes go into some of the non-experimental models like correlation models that you might use. And the book, it addresses those as well. The next objective from part 2 I wanted to address is are classifying examples of pre-experimental research designs. So I wanted to go over a little bit about what some of these, a little bit more detail about pre-experimental designs. So to illustrate this, I want to talk about, I want to just use as my example the topic of students using AI tools in the classroom. So artificial intelligence represents one of the latest forms of technology that teachers are now sort of grappling with in terms of how they might want to use it as a tool for their students, ostensibly inside the classroom. So if you wanted to do some research on AI in the classroom and you wanted to do some pre-experimental research, you might consider a one-shot case study. And this type of study is a very weak experimental design. It involves one group, so that might here my silhouette of a student at the computer represents a group of students using AI in the classroom. And so you as a researcher or as a teacher would provide AI tools to the students, and then you would make observations about how they use it and collect data like perhaps some achievement data, perhaps data related to their attitudes about it or other things. There's definitely some valuable information that you could get by doing a careful, simple one-shot case study. So that's one pre-experimental model. Another one would be the one-group pre-test, post-test. And that would be just to measure the potential efficacy of AI in the classroom. You would give students a pre-test over something, some skills related to a particular topic. You'd implement some AI-related tools as part of their instruction, and then you would post-test them and look for any gains so that at least you could determine whether or not all your choices about students using AI in the classroom and your decisions as an educator impacted between the pre-test and the post-test what you wanted students to learn. So that would be a one-group pre-test, post-test. Again, it's a very weak experimental design, but it is a design that could be easily done in the classroom. Now we have another model is called the static group comparison, and in the static group comparison, again another weak experimental design. It involves two non-equivalent groups, and by non-equivalent groups I mean groups that were static. That is, they were intact. They weren't selected for to be randomly in those groups. So they're non-equivalent. And the my two icons there represent perhaps a class of students who are given AI tools, and a class of students indicated by the student who's just got their hands in the air jumping for joy because they're not tied to technology chains in the classroom. That would be the non-AI group. And so, again, a design like this might involve two classes, one given AI and the other class not given AI. And then you test them after a certain amount of time over the skills that you're hoping to measure, and you're looking for differences. Now, obviously, you could find a lot wrong with this model if you do get differences between those two groups. There are a lot of factors other than AI that might have contributed to that, but sometimes this is the only way that you can study such a phenomenon. So this is called a static group comparison design. Another one is similar design, but it's got a pretest associated with it. So we have our two groups. They're both pre-tested over some information, some topics, and then they're post-tested. Notice the importance in this case of a pretest, because it's possible between the two groups when we looked at the static group post-test only, it's possible that the two classes represented two populations of students who had very different backgrounds related to the topics or the content that was being addressed, and so pre-testing them in advance could be really important. So just pointing that out. So those were the pre-experimental designs, and now I wanted to go into examples of experimental research designs. And none of these are weak designs. These are all strong experimental designs. So any design that includes randomized groups or randomized subjects into groups would be considered have the potential to be experimental. So in the randomized post-test only control group, you have a population of students. Here they are. They're all, look at them. They're all free, running around, free from the chains of whatever. And then we're going to randomly select half of them from the same population, and then we're going to put them into groups. So now we randomly selected two groups. They weren't put into two. We didn't just pick classes. We randomly selected from the entire subpopulation, and now we give them a treatment. In this case, AI versus no AI tools, and then we post test them. So this is the randomized post-test only control group. You can guess what the randomized pre-test post-test control group is going to be. Again, notice that these are groups that were randomly assigned one or the other treatment, to be in one or the other groups. And one of the groups is given the treatment, the AI. The other group, our control group, is not. And they're both given a pretest to see where they're at with respect to the skills they're trying to learn, and then they're post-tested. And you would examine the difference in pretest to post-test scores as your primary dependent measure. Now, one problem with pretesting is that it can often cue learners to things that make it so that they're going to do better on the post-test regardless of what happens, regardless of whether they have an AI tool or anything else. It's a very common factor. It's called the testing effect. And basically it means that if you take a test, regardless of your performance on it, if you take that test again, you're going to do better on it. And regardless of what happened between one take and the other, it just happens to be a statistical sort of pattern that's observed. Well, there is a way around that, and it's a type of factorial design called a randomized Solomon 4 group. So in this case, you actually create 4 groups. They're all the participants are randomly assigned to each of the groups. Half of them get the AI treatment, half of them are no AI, and in each of the treatment groups, half of one group gets the pretest and half doesn't. And in the non-AI group, half gets the pretest and half don't. So here you'd have our two groups together would be the AI group versus the non-AI, but then you can also analyze the data based on which groups had the pretest and which didn't. And in this way, in your data analysis, you could determine whether or not there was a pretest effect on anybody and determine the extent to what that effect was. And that could help you more clearly identify what impact your your treatment had, if there was a difference in that case. So the randomized Solomon 4 group can be very effective if you're concerned about the testing effect. And finally, the last experimental group design that I wanted to address is factorial. And in factorial, again, the Solomon 4 group would be considered a type of factorial, but in this case, I'm going to use a factorial that involves another variable. So let's pretend that I'm doing a study and I want to test students who get AI tools versus the same types of students who don't. They're randomly selected, put into groups. But I also want to test whether or not there's a difference in whether kids work in groups or they don't work in groups in both factors, in both the AI group and the non-AI group. So in this case, I've got individual students working on the instruction versus groups of students working, and then I would be able to compare and do multiple comparisons. In this case, I could compare, going back, and then I could also have gender as another variable that I observe. So I have females versus males, because maybe for whatever grade level I'm observing, maybe I'm interested in group work. And based on the literature review, I discovered that the constitution of the groups is the effectiveness of those is really dependent on gender. And so gender could be another factor in my study, and that would be a grouping variable. And if I have all of those subgroups, then I can compare males versus females. I can compare males working in groups with females working in groups. I can compare everybody working with AI versus everybody not working. I can compare males and AI versus males and not AI. I could do all kinds of comparisons and look for things called interactions to find out whether or not any of those variables influence or affect the others. So in this case, we would call that design a 2 by 2 by 2 factorial. And our 2 by 2 by 2 would be gender would be 2, whether they're a group or an individual would be 2 groups, and whether they are getting AI tools or not would be 2 groups. So altogether, I would have 8 different groups total that I could look for interactions on. So the next group of designs that are related to in the positivist model would be quasi-experimental. And quasi-experimental are very similar to the experimental, except random assignment is not done, and or I should say random assignment is manipulated. So let's look at that in some degree. So here, matching is a form of quasi-experimental, and matching is done where the subjects are actually matched first on some factor in the population, and then they're randomly assigned. Each match is randomly assigned. So I'll tell you a really good example of when this is important. If you wanted to assign 2 groups, you don't have a huge population to choose from, but you want to randomly assign groups the best you can. However, you want to make sure that achievement levels are adequately dispersed and equally dispersed in each group, because you don't want to just randomly end up with all of the higher achievers in one group and all of the lower achievers in the other. Even though it's not probable, it might be likely if you have a lower population to choose from. So in this case, you could match students by achievement and then randomly select from one to go into one of your one group and one to go in the other. So that's an example of matching. Again, a quasi-experimental design. The next quasi-experimental is counterbalanced, and that is a design where all the groups receive all the treatments, but each group receives the treatments in a different order. So in this case, whether the groups are randomly assigned or not, and in fact, this could work better if the groups aren't randomly assigned. If you're looking at intact classes, for example, or you're pulling from students in the same class, and you want all the students to be able to benefit from the treatment because you believe in your hypothesis that it's going to be beneficial and you want everybody to get it, then in this case, half the class could get the treatment and be measured, and then the other half does it, and then you switch. So that's a counterbalance design. And then there's a time series design in which one group is there's an intact group on the left, and you take their temperature or you measure something related to what you're interested in terms of achievement, and then you implement something to that group like AI, and then you continue to take achievement measures all along the way. And so you end up with a series of measures for the same group, and then you go in and statistically look at the pattern of performance, if you're measuring performance, and whether or not the moment when you introduced the treatment, those patterns changed. And that's one example of a time series design. There's other examples of those too, but that is another example of a time series design. Now, the last thing I wanted to talk about, and it relates to some of these experimental designs, has to do with the validity of why you use certain designs and what validity means. And one thing that's confusing about some of the objectives for part 2 of the class is that the word validity is associated with some very different concepts. We use the term validity as part of internal validity, external validity, threats to validity, and then there's construct validity. And so I'm going to talk a little bit about some of these. I will just say about internal and external validity that the big difference there is that internal validity addresses your ability to speak with confidence that your treatment actually caused some differences. And so we're in this case, we are talking about causality. External validity actually means something completely different. It means how generalizable are your results to populations that aren't your experimental populations. So that's very different. Now, one of the objectives related to validity is your ability to explain the difference between type 1 and type 2 errors and identify common strategies used to minimize those errors. That means improve your internal validity. So in going over the type of error, a type 1 error is made when you collect your data and you believe that your treatment had an impact on your dependent measure, but in reality it didn't. Your data shows that it does, but in reality it didn't. A type 2 error is a false negative where your results indicate that your treatment didn't have an impact on your subjects, but in reality it really did, or it would if you tested it under some different condition, or there was a problem with the design and you ended up with results that did not show significant differences, but in reality there would have been. So let me show you a specific example of this. Let's say that you had a randomized pretest post-test control group design, and you had a variable that was a reading buddy variable that you were going to test with some students at a school, all at a school. So they were going to do a reading buddy program in primary grades, but it was going to be an AI reading buddy. And then some other schools weren't going to get that, and it's going to be pretest post-test. And so you're working in a district, and the only way that this is going to work is if you assign each school from your district either they're all a reading AI reading buddy school or they're not. So in this case, you have 12 schools and 6 of them are assigned the reading buddies and 6 aren't. And let's say you can even decide where you randomly picked the schools to be in one of the 2 groups. All right, and you also notice that the schools, their enrollment in the primary grades is pretty even. In fact, very, very close to each other. Okay, so your population sizes between the 2 groups are pretty big. And so let's say that you have this and you test it at the end of the year, you test everybody and you find out that all the students who got the AI reading buddy, their post-test, the differences between pre-test and post-test were significantly better than the control group, okay? However, one thing that you didn't note in your study was that you, just by chance, you happen to have 2 schools who were in the reading buddy group that had a lot of migrant migrant families were in those schools, and the migrant kids, they were ELL students, English language learner students, and they just typically scored lower anyway on everything. They would score lower on the pre-test and the post-test. But between the beginning of the study and the end, the families actually left. They moved away. And so those students weren't in the study. So their pre-test scores were eliminated, and so were their post-test. So your overall population size was lower, and the students who were left behind were the ones who actually had higher scores. And so your results were skewed. So in this case, you'd have a false positive or a type 1 error because the students, because of mortality. That's a threat to internal validity, where you lost enough subjects to actually make a difference. So you'd have to redo this study or do some kind of statistical thing where you might be able to balance things out. I'm not exactly sure what would be the best approach there. Okay, I want to talk then about Objective 2.9, which is to explain common ways to establish construct validity. So this is a completely different use of the word validity. It has really nothing to do with internal validity or external validity, but it's something really important in education, and it has to do with measuring variables and with operational definitions. Okay, so let's take a look at construct validity. So construct validity examines how well a given measurement scale or measurement in general is measuring this construct that it's supposed to measure. And there's generally two categories of construct validity assessment, and that is theoretical and empirical. Theoretical relies on expert judgment, and empirical relies on data. So let's just focus on two different ways to measure construct validity. So we'll look at, first of all, we'll look at the construct of happiness, okay? So happiness is a construct. There isn't something you can point to and say, that is happiness. This is a cup of happiness. Although I suppose I can point to something that is a cup of something and say, that will make me happier. But that's for another day. So happiness is a construct, okay? And let's say that you wanted to measure happiness levels because, let's say, you wanted to do it as an educator, and you want your students to be happy. You want the experiences they have in your class to make them happy. So a theoretical way of determining whether or not how you're going to measure happiness is using a scale is called face validity, and that's where you would create a scale like we have here, and you could just look at that scale and say, if I were to give this to students and say, mark on here your level of happiness today, circle the face that represents where you're at in terms of happiness. You could look at that and just say, just as a rational thinking adult, that would be a good way to measure happiness without any other tests. It seems that something like that would have pretty high face validity. It's also a way that experts could weigh in on it. You could give this to a psychology expert, also known as a psychologist, and say, is this a good way to measure levels of happiness in your expert opinion? Now, another theoretical way to measure the validity of a construct is something called content validity. And that's where, let's say that instead of a happy faces, you wanted students to report a level of agreement to a statement, content. Some people are generally very happy. They enjoy life regardless of what is going on, getting the most out of everything. To what extent does this characterization describe you? So again, you could look at that and you could give it to an expert, maybe a psychologist, and say, does this do a good job of measuring a degree or level of happiness? And the expert could tell you the reasons why it does or doesn't. And one thing about content is, depending on the age level of the people responding to this who have to read it, an expert could look at the language and say, you know what, I don't think that the students who are going to be reading this are going to understand what getting the most out of everything means. They're too young for that. So you need to change the language. So that would be an example of trying to maximize validity by editing it based on a content expert. And in this case, the content would be an expert at reading comprehension for that age group. So that's another theoretical way of establishing some content validity. Now, there are empirical ways that you can determine validity. And again, by empirical, we're talking about making observations about something. So and the first one I wanted to talk about is convergent validity. And convergent validity refers to the closeness with which a measure relates to or converges on the construct that it's supposed to measure. So it can be established by comparing the observed values of one indicator with that's measuring the same construct with how well the respondent responds to the other value, and you can correlate those two. You're assuming that both of them measure the same construct, and if they do, then you're going to have a strong convergence. If you rate very happy on the faces, you'll rate an 8, 9, or 10 on the statement, and with very unhappy, it would be the opposite of that. We also have another empirical model called discriminant validity. And that refers to the degree to which a measure does not measure, or it discriminates from other constructs that it's not supposed to measure. So it's demonstrated that indicators of one construct are dissimilar from or have low correlation with others. So in other words, you could have students, you could have your subjects respond to how they're feeling right now about something with the scale, and then you could ask them their level of happiness, and you would imagine, you could make the assumption that they should not be equal, that a very happy should be more in the okay or maybe a little worried, and not the freaking out or panic, not the 5. So those should not correlate with each other, or they should have a negative correlation. Then there's another way that you can empirically test a construct, and that's predictive validity. And that's the degree to which a measure successfully predicts a future outcome. And this is an extreme measure, but I'll just show you. So you could predict that somebody, the students who circle very happy consistently have a less chance in the future of going on Zoloft or having depressive episodes. You could just make that prediction if that's a good measure. A more realistic one would be the SAT scores. The reason why colleges use SAT scores as admissions criteria is that the higher SAT score you have, that correlates very well with your possible success in college. That doesn't mean that if you have lower scores, you're not going to be successful. It just means that those two variables correlate pretty well with each other, and that's why they're used. And finally, there's concurrent validity. And concurrent validity examines how well one measure relates to another criteria that should occur simultaneously. And by simultaneously, so you have a group of subjects who are doing something, and while they're doing it, you give them, you say, hey, you have them circle the face that matches their mood, and then you're sitting there with a clipboard, and you're identifying the behavior of the subjects who are doing something, and you can identify just based on their behaviors whether they appear to be happy or sad or indifferent, and you can rate each person at the time that they are asked to rate their mood. And then you can correlate those two. So that's an example of concurrent validity. And hopefully elaborating a bit on some of the key objectives for Part 2 will help you better understand all the material for this phase of the course. And I hope that you will rate a very happy when you're finished with exam number 2, because you feel so confident that you did really well on it.